SwayamPrabha. Digital India. Educated India.
Alright, so this will be our last session on photoelasticity. So today I will discuss a little bit more about the standard calibration procedure for getting the photoelastic material constants, and I will also talk a little bit about reflection photoelasticity. So everything we have done so far is in transmitted light, which is great if the object that you are measuring the stresses in is optically transparent, but in most engineering applications you do not have that luxury, unfortunately. So reflected photoelasticity is another method that has emerged more recently, I would say, compared to conventional transmission photoelasticity to work mainly with engineering structures, right. So we will talk a little bit about that. The algorithms are somewhat similar, except there is a strain optic law and surface stress optic law and so on, but the schemes are nearly identical. So before we go there, let me just backtrack and see where we were. We had this summary of how to obtain the stresses. So if you take a look at this, we had 4 steps that we had outlined. The first is to use this. You have an object, of course, you start with something that is loaded. So this is your object that is loaded right here, and then you have a white light source that is placed over here, and you have a linear polarizer in front of the light source, and then the light, polarized light, plane polarized light is allowed to pass through the object, interact with the stress field, and then it comes back out, and then you have a crossed analyzer to look at the light that is coming through, right. And like I mentioned, this has to be done at every point. So the isoclinics, for instance, will give you orientations at every point inside the object, especially varying stresses, and so by rotating this polarizer analyzer sheet you can get these fringes to move, the dark fringes. When the dark fringe, the first step will be to see when a dark fringe passes through any given point. So let us say you want to get the stress at a particular location, you rotate the polarizer analyzer pair, and at a particular location one dark fringe which was nearby starts moving, I suppose, and then it passes through the point of interest, or a bright fringe passes through the point of interest. The calculation is analogous. At that point the value of the principal stress orientation, the direction of the principal stress orientation is given by the angle that the polarizer makes with the horizontal line at that point, right. So by rotating this for every single point for all 5 values, you can get a map of the principal stress orientations for the stressed body, right. So that was the first step. After this, we said the isoclinics have done their job. After this, their information that you can use about the orientation of the principal stress is already obtained, and so the next step is to get rid of the principle of the isoclinics, because they interfere with your light source, with your interpretation of the actual stress values. So for this we saw that you could use a circular polariscope, which basically has 2 quarter wave plates, after the one after the polarizer and one before the analyzer, and we discussed what this quarter wave plate does, and then we saw that the resulting intensity goes like sin square delta by 2, okay, delta being a function of the wavelength of the incident light and the magnitude of the difference of the principal stresses, right. So we had discussed this formulation in the last couple of classes, and the method we use for getting rid of the isoclinics is of course to just get the circular polariscope in the first place. So you only see isochromatics after this, and now at the particular point x comma y where you want to get the principal stress difference, you place the polarizer along the principal stress direction, right. From point 1 you know the orientation of the principal stress directions at each point, you place the polarizer in that direction, and then if you shift to monochromatic light you will get dark bands, which are basically the isochromatics but fixed wavelength. So you will get only dark bands, and then you rotate the analyzer with respect to the polarizer from perpendicular, you rotate them by some angle beta, and then we worked out the algebra for what the final result will look like using the rotation matrix. And if you do that for a dark fringe, you will get this condition, and this will correspond to delta equal to 2 times beta, right. So when you keep rotating by some angle beta. When beta becomes delta by 2, you will get a dark fringe, and you know the value of delta, and from there, since you know the wavelength of light, delta being a function of these two, you can get the value of the principal stress difference, right. And I also mentioned that this technique of using the polarizer and analyzer in this way by changing their relative orientation is called Tardy compensation. I mentioned this in the last class. And then once this is done, you know the principal stress direction, you know the principal stress difference, you then have to go and actually get the fringe orders, okay, and the fringe order is given by delta by 2 pi. You know delta now, right. So now the stage is set to go and get sigma 1 minus sigma 2 from delta. The only complication here is that delta is a has this integer n sitting inside the fringe order, remember, because you have multiple isochromatics, or in this case multiple dark bands. And so to figure out which n value you are actually dealing with, you have to do something called fringe ordering or fringe counting, and for that you first write down what the fringe order is in terms of delta by 2 pi, that is written in terms of the stress optic coefficient and the principal stress difference. And so if you know h, of course, because of the thickness of the sample, you know lambda is wavelength of light, you need to know what c is. If you do, then you can get sigma 1 minus sigma 2 if n is known, right. So if you can count the fringes, if your point x comma y lies in the 5th fringe or the 6th fringe, then n is 5 or 6, and if you know the other constants, you can get sigma 1 minus sigma 2, okay. For purposes of notation, we call this lambda by c ratio that is here as f sigma, right, and this is a material constant for a given wavelength, right. Now the final step in this is, if you did not know what f sigma was, or if you did not know the photoelastic parameters for the particular material, then you have to calibrate, right. So you have to use a standard loading condition and then apply the loads as per this standard loading condition, where you know what the stress field is and you can physically see what the fringe order is. So you know n, you know sigma 1 minus sigma 2 from some analytical calculation, from some model or theory or whatever. If you know that, then it is a simple process of inverting, and you know h, it is a simple process of inverting to get lambda by c, okay. So you can get f sigma first by calibrating a given material, given photoelastic material, and you use that for getting the sigma 1 minus sigma 2 value, okay. So these are the 4 basic steps that you will use in determining the actual stress fields, the orientation first and then the principal stress difference after that, okay. Now I will talk a little bit about this calibration procedure, which is number 4 today. Using this diametrically loaded disc, that is a standard procedure, and it is a very simple procedure because it is very reproducible, and the solution is well known. If you take a course on elasticity or solid mechanics, you will be able to work out the solution by yourself. Nonetheless, I will tell you what the solution looks like, and then we can take it from there and see how to use it. So this is basically just a cylinder, very thin cylinder disc like this, and it is loaded exactly along the diameter by a load F, okay. This is the force. So from theory of elasticity, you can get the stress tensor at every point. The calculation is fairly straightforward, if it is a little bit tedious. It needs superposition of 3 different stress fields, something called a Boussinesq solution. The details are irrelevant, but basically it is a well known solution, and specifically you look at the origin, which is the center of the circle of the cylinder. The solution here gives that the principal stress difference at the origin is 8f by pi d h, okay, d being the diameter, radius is d by 2, okay. So, from this elasticity solution we know that the principal stress difference is 8 f by pi dh, and this is nothing but n times f, what we called f sigma by h from before. If you go back here, this was f sigma inverse. So, n f sigma by h is sigma 1 minus sigma 2, right. So, sigma 1 minus sigma 2 is n f sigma by h. So, h cancels out and you get f sigma is 8 f by pi n d. Okay, so, this is how you get the value of the parameters for this, the material parameters for this particular case. Okay. Now, like I said, there is some deal to do with the fringe counting. So, you need to figure out what n to use, because for all integer values of n, the sigma 1 minus sigma 2 will give you a dark band or a light band, right, depending on whether you have a light field or a dark field. So, you have to do fringe counting. So, to do fringe counting, you start from a location where sigma 1 minus sigma 2 is very small. You need to know this a priori, okay. And this gets assigned to n equal to 0, okay, or n equal to 1 depending on where it is. I will show you an example for this diametrically loaded disk in a minute, but this basically gives you the first fringe, and then successively light or dark bands correspond to n equal to 1, 2, 3 and so on. Of course, if you have a light band, then you have integer n for a light field, for a bright field image. If you have dark band, you have integer n for a dark field image. Okay. So, just make sure that that distinction is clear. Otherwise you can just count, increase count from this location, and usually this location occurs in a practical problem near a stress free boundary. So, if you are using this to study cracks and so on, you would usually get the 0th order fringe very close to either the crack tip or the lateral faces and so on. Okay. So, that is basically what you have to do. So, now I will show you an image taken from a reference that depicts these fringes and demonstrates how you can do this fringe counting. Okay. So, here is the geometry of this diametrically loaded disk. This is our this is our coordinate system. You have x and y as usual, and then the load here is denoted p, but we have used f, does not matter. And at a particular point, let us say here on the x axis you have principal stress directions like this, and obviously the directions of the principal stresses are going to change from point to point. That depends on where the the isoclinics will give you information about that. We have already seen this. If you take the individual principal stresses for this known solution from elasticity, this guy, and you plot the principal stresses, you will get them to look something like this. So, that the difference in the principal stresses looks like the red line. Okay, that is the first point we want to make sure, and the horizontal direction is normalized with respect to r, which is the radius, which is d by 2, and is calling that zeta to go from -1 to 1. Okay. Now, you notice that sigma 1 minus sigma 2 is 0 very close to the free boundary, which is this end and this end. Okay. And the advantage of that is that sigma 1 minus sigma 2 being proportional to n, remember the formula we had, remember that sigma 1 minus sigma 2 was n f sigma by h. So, the sigma 1 minus sigma 2 is proportional to n, which means if sigma 1 minus sigma 2 is very small, then n is also small. So, the 0th order fringe comes at the outer boundaries. Okay. The highest fringe order, if you are going along this horizontal diameter direction from the outward to the inside, the highest fringe order should come in the middle, because that is where sigma 1 minus sigma 2 has its largest value. Okay. So, you can use this idea, and if you take a photoelastic image of this, now this is your force F here, you see fringes like this. Okay, this is typically what you will see if you get a diametrically loaded disc. You will notice that this is monochromatic light, it is a green light source, and it is also using a circular polarizer. So, there is a polarizer sheet, circular polarizer, there is a polarizer sheet, and then there is a quarter wave plate, and there is another quarter wave plate in front and analyzer sheet that is crossed with it. Okay. This is a bright field image, because the area around the disc is bright. If you had a dark field image, this region will be dark, the dark bands will become bright and the bright bands will become dark, right, that is the only change. So, we will work with a bright field image. In a bright field image, the dark parts or the dark fringes correspond to half integer values. In a dark field, they correspond to integer values, and the opposite happens with the bright areas, right. Good. So, if you want to look at the fringe counting, remember we said that the fringe order is lowest at the left and the right end. So, you have to start from there and then go inward and do the counting. Okay. So, that is what I have shown here. So, you have 0, the 0th order fringe first over here. Remember, this is a bright field image. So, the bright areas are integer fringes, dark areas are half integer. Okay. Please keep that in mind. So, then we start from here, you get 0, 1, 2, 3, 4, 5, 6, 7. So, this is where the origin of the circle is, and that lies in the 7th fringe. Okay. Sigma 1 minus sigma 2 is 0. So, you have n equal to 0 here. So, you have the 7th fringe. So, you have to use n equal to 7, and you can calculate f sigma is equal to 8f by pi n d. You know d, you know f, because that is the load you have applied. You know now n, which is equal to 7, and you obviously know what 8 by pi is, right. So, you can calculate the material constant. So, now you have calibrated your sample, right. You have calibrated the material, you know what the material constant is. Now, if you have any other situation, you can go back and use this value of f sigma. The most common way of doing this calibration, of course, in a practical sense, is to plot the fringe order n as a function of load, or load as a function of fringe order. So, your f is on the x axis and your fringe order is on the y axis. So, you increase the load from 0, keep going up, and then you see which fringe is right in the middle. Obviously, the fringes will all move around. So, you will get something like this, then you put a best fit line, slope of the line will give you pi d f sigma by 8. Again, you know what pi d by 8 is, because you know d, and you can calculate f sigma. Okay. So, you can use this technique for a whole bunch of other things. Once you know what the material constant is, you can use it for bending of cantilever beams, or 3-point bending, fracture toughness estimation, stress intensity estimation, things like that. Okay. So, it is a very standard way to do this. Okay. So, that sort of summarizes all 4 steps. So, that if you know how to count the fringes coming from outside, it summarizes the entire sequence of steps you have to do to get a stress field. Remember, you are only calculating sigma 1 minus sigma 2. So, in principle you can superimpose a hydrostatic pressure and you will not see a change in the fringe pattern if it is purely elastic, but nonetheless you will get a full field recovery for a plane stress deformation problem. Now, the mathematics is fairly simple, the algebra involves some matrix manipulation and so on, but we should be able to calculate given any situation the stresses in a particular object, at least the principal stress difference and the orientation of the principal stress directions. Alright, now there are a few limitations of course naturally with this entire method. The first limitation is that you obviously need a transparent stress birefringent material. And that means that you can't do this with metals for example, or you can't do this with opaque polymers that are not birefringent, and so you have to worry about making an analog of the actual model being tested and make sure that the conditions under which it is being loaded are analogous, identical and so on, right. So, that is one obvious limitation. The second one is this need for plane stress. Now, we have discussed only a plane stress case, there is something called integrated photoelasticity. That somewhat mitigates this limitation. So, it basically calculates a 3-dimensional stress field with some approximations thrown in, but again that is beyond the scope of what we can discuss here, but there are some standard references that you can look to. One very classical reference is this book by Aben, H. Aben, it is called Photoelasticity of Glass. Aben was one of the pioneers of this technique of integrated photoelasticity. The to some degree, so to some degree you can get rid of this plane stress limitation, right, even though there are some assumptions that you have to make and so on, you can still work around it. The transparent need for a transparent material, one more recent way like I mentioned at the start to get around this is to do something called reflection photoelasticity. Okay. Now, I will talk a little bit about this, I will introduce the basic idea and sort of sketch out the basic equation, and then we will conclude our discussion of photoelasticity itself with this. But let us see what this reflection photoelasticity is. Before we stop, naturally the name sort of gives it away, right. The idea is very simple. So, if you have an opaque material, then you basically coat, let us say this is my opaque material and I want to evaluate what strains or what stresses this material is being subject to. I coat it with a birefringent transparent material and I coat it in such a way that there is perfect bonding at the interface between the two, and then I apply my loads to this sample, and if the bonding is perfect then there is no net slip or displacement difference between the two interfaces. So, all the load over here is being transmitted to this guy and that guy is being squeezed, right. Now, the idea is you pass light same like you used to do before, you pass light like this, it comes back and then you have a polarizer analyzer sheet and then you look at it. So, you put a polarizer sheet here, you put your analyzer sheet here and then you look at the same thing, okay. Instead of doing it in transmitting mode, you do it in reflected mode. Now, obviously you can't have this beam exactly perpendicular, because if you did then the polarizer and the analyzer will coincide, right. So, there is usually a small angle that is given, very mild angle. So, you actually need a fair distance from the imaging system to the surface. So, you will often see people use high zoom lenses for doing reflection photoelasticity, and this small deviation gets amplified over a longer distance and you have an analyzer polarizer pair again as usual, and you finally see what the reflected field intensity looks like, okay. You will again get fringes in this material, and the interpretation of the fringes is similar to what you have in the transmission case. Okay. The only small difference, there are quite a few approximations that go into this. Again, I am not going to detail this entire method for you, but there is something called the strain optic law, which is used in this case. So, now you have, this is a layer, let us call this a coating. So, now you have the difference between the principal strains epsilon 1 coating minus epsilon 2 coating, and this is given by some other material constant times the thickness of the coating. So, this is coating thickness, this is some material property, epsilon is a subscript, right, f epsilon, and you have this. Okay. If the material is elastic, which you assume it is, then the stress, principal stress difference in the coating is given by Hooke's law, which is E c by 1 plus mu c. Again, the subscript c indicates coating or layer times epsilon 1 c minus epsilon 2 c. Nu is the Poisson ratio. This is E c is a coating Young's modulus, of course, E. And so, you will get the principal stress difference. You will get isochromatics just as before and isoclinics just as before, and you will do the same type of thing as before, but now you will get principal stress difference in terms of the principal strain difference. Okay. And then what you have to do is the stress in this. So, this is our specimen. So, the principal stress difference in the specimen, which I will give a superscript S, is in the same ratio as that with the coating. Okay. Because the displacements that are transmitted from here to here are the same. So, the strains that are transmitted are the same. So, the stresses are in the ratio of their elastic constants. So, from here you can get sigma 1 s minus sigma 2 s. Okay. And you have to do the same thing as we did before. So, there really is nothing more to this than what we have discussed. The most important thing is that the coating thickness must be kept reasonably tight, and so usually people use between 1 and 5 mm of thickness. You have to make sure that the film is uniform, so that you do not have any thickness effects in the film, you do not have any variation in the principal strain difference because of thickness variation, and so usually people will spin coat or dip coat or do things like that, and you can then use this for measuring the strains in the sample and the stresses in the sample. Okay. So, with that we sort of come to the end of this discussion on photoelasticity. We started off by looking at some of the properties of transmitted light, why it bends, why it refracts, why do you have birefringence and so on, and then I also introduced this idea of stress induced birefringence, where the presence of a stress field can actually change the refractive index in two directions due to the stress optic law, and then from there we slowly built up these little units which allowed us to interpret the effects of things like polarizers and analyzers and quarter wave plates and things like that, and then this Jones algebra allowed us to put all of them together in the form of rotation matrices and evaluate the net retardation as the light comes out from the analyzer sheet, right. And then we also worked out these 4 standard steps that you will have to go through to do any such measurement in photoelasticity, including calibration using a standard test geometry like the diametrically loaded disc, and finally this idea that you can use the reflection of this light through a birefringent material also to evaluate the stress field is something that is exploited in reflection photoelasticity. Okay. So, with this we will sort of wrap up our discussion of photoelasticity. It is a very useful technique, but it is not a technique that is all encompassing, which means you can't just go and apply it to all situations. You have to make sure the stuff is plane stress, you have to make sure that you have birefringent coating or you have birefringent sample and things like that. And so, it is a little bit limited in what it can do. The next technique we will discuss is called optical tomography, specifically X-ray tomography, and that really is something that you can use for a whole variety of situations. Right? It relies on very few assumptions and very few constraints. It uses several geometries that you can exploit. We will discuss a few of these geometries and how to interpret data in that context, but it is a much more broader and more widely applicable technique, and it is also reflected in the fact that tomography is used from brain scans to radiography and airport scanning and so on, right. So, we will start the next session with a discussion of optical tomography.